Hello guys, welcome to Crown Smart. In this video, we want to talk about algebra. Okay, algebra in Lebesgue measure. Now, let X be an arbitrary non-empty set. Okay, and let P of X denote the power set of X. Now, we say that the class, which looks like a fancy A, which is a subset of this power set, is an algebra of subset of X if and only if this satisfies the following axioms or properties. Now, one of the properties is that the empty set must be in this class. Okay. Secondly, if if E is an element in this class, then this implies that E complement must be an element in this class. And lastly, if G is in this class, then this implies that the finite union of E union G is also what? In this class. Okay, so once these three conditions are satisfied, then therefore we call this an algebra of subset of what? Of X. Okay, X is an arbitrary set. So an example of an arbitrary set is set of real numbers R. Now, also in some textbook for this condition tree, we can say that if I don't want to write it this way, this one is just saying finite union. Okay, so if you pick any two sets and you now do their union, two sets in this algebra, and you now do their union, and their union is inside the algebra, then it satisfies condition 3. Sometimes you might see if a finite sequence, let's say finite sequence of I equal to 1 to n is a subset of what? This class, then this implies that their finite union I equal to 1 to n of EI is also what? In this. So this is also an extension of condition 3, which is also the same thing. Okay, so this could be a sequence or a set. Okay, now let's give an example. An example is that, let's say this is the collection of finite union of disjoint interval. Please don't mind my handwriting. So let's say this is an algebra. This is a finite union of disjoint interval of R. Sorry, intervals of what? R. Of R, the set of real numbers. Okay, so this is a class. So this class is said to be an algebra. Now, for us to show that this is an algebra, we need to show that it satisfies what? These three conditions. Okay, now remember, what do you understand by disjoint interval? Now, an interval is said to be disjoint if the intersection is what? Empty. So two sets are said to be disjoint if the intersection are what? Empty. So we can have an interval, let's say 1, 2 intersects 3, 4. Of course, the intersection of this is what? Empty. Okay, so that's what we mean by disjoint interval. Now, when you now say finite, it means that you can count the number of intervals you are using. So there are finite number of them. Actually, most of them you might not be able to count them, but it has a finite value. Okay, now let's show that it's an algebra. Now let's say, now know that for the first condition, we know that an empty set can be written as A, A. Okay, an empty set can be written in this form. Of course, what this means is A is strictly less than X and X is strictly less than A. Is that possible? This is a false statement, so this is what? An empty. It's just like saying 2 is less than X and X is less than 2. It doesn't make sense, right? So this is what? An empty. Also, you can say an empty set is also A is less than, okay, let's use B, comma, this is also an empty set. Okay, and also an empty set can also be written as this way. Okay, let's say, of course, this is also what? An empty set. But if you take their union of this, if I do A comma A union B comma this union C comma this, okay, if I do their union, I will still have what? Empty set, because this is already an empty, this is already an empty, this is already an empty. So union of empty set will still give me what? Empty set. Observe that these intervals are what? Are disjoint. Disjoint in the sense that this union, this intersect, this is empty, this intersect, this is empty. Okay, now their union are what? Finite. Their union are what? Are finite. Okay, so you see that this gives me what? An empty set. So therefore the empty set is what? Is in the algebra. So this implies that the empty set is in what? This algebra, because this is the set of finite union of what? Disjoint interval. So this is a finite union of disjoint interval, therefore it is inside what? This class. Now secondly, we need to show that if we pick a disjoint interval or an interval in R, okay, then its complement is also in what? In that class. Okay, so let's say this is a real line from minus infinity to infinity. Let me create an arbitrary interval AB. Okay, now if this is an interval AB, which is A comma B, let me call this set A to be A comma B, or let me use set E. Let me use the E to be A comma B. Now, what is the complement of this interval? Now, what is the complement? The complement here is simply E complement is all those elements that are not in this interval, but they are outside what? They are outside the interval, and those elements that are outside the interval are in what? Are in R. This is a set of real lines. So the complement is simply minus infinity to what? To A. Remember that A here is not included, so A here will be included. Okay, union, that is, this is the complement, this is the what? The complement. Union B to what? Positive infinity, and this is what? My E complement. Now observe that these two intervals are disjoint. Why are they disjoint? If you do this intersect this, it will give you what? Empty, because the element in this interval is not here. Okay, so their intersection is what? Empty. And observe that their union is what? Finite. Okay, so this is just two intervals, so it's finite. Okay, so therefore it is in the what? In the algebra, because our algebra by definition is saying finite union of disjoint what? Interval. So once I can find a finite union of disjoint interval, then it is inside this algebra, because you are saying that this algebra contains finite union of what? Disjoint interval. So the complement is also what? In it. Now the last one, we want to show that if we pick any two, if we pick any two interval and do their union, then it is also what? In the algebra. Now observe that looking at this now, or we can say the finite union of we can actually say the finite, remember this condition, the third one, we say if we pick any two in this algebra, you can also show that their union is also in the algebra, right? Or we can say finite, if we can find a finite set, okay, a finite sequence which is a subset of the algebra, then their finite union is also in algebra. So this finite union is trying to say that it might not only be two sets, it can be more than two. Okay, you can have 3, 4, 5, 6, 7, so far they are all what? Finite. So if you look here now, let's go back to our number 2 here. Observe that this is an interval, right? This is another interval, which is this side. This one is another interval, which is this side. So if you do their union, okay, if you do this union, this, what do you have? You have we have the whole set R, right? And the whole set is in the what? Algebra. Okay, the whole set is in the algebra. So their finite union is already what? In the algebra. Remember, if you do this side union this side union this side, you are having what? The whole set R. Now the whole set R is in the algebra. Do you know why the whole set R is in the algebra? Because we agree that the empty set is in the algebra. We agree that the empty set in the algebra. So therefore the complement of the empty set must also be what? In the algebra. And what is the complement of the empty set? R. So if R is in the algebra, therefore their finite union is also what? In the algebra. So we have satisfied the condition what? 3. Now I want to do a proposition. Okay, now the proposition says that if A is an algebra, now the proposition says that if A is an algebra, okay, of subset of R, and R is in okay, no, sorry. Now look at the proposition now. It says if A is an algebra, then the following condition holds. The first condition holds that R is in the algebra. Second condition says that if A, B is in the algebra, this implies that A intersect B is also in this algebra. And the third condition says that if the same AB is in the algebra, then this implies that A difference B is also what? In the algebra. Okay, we want to show this proposition. Of course, I've already shown the first one, but I will still do it again. Okay, now remember the rules of a class to be an algebra. For a class to be an algebra, then the class must satisfy these 3 basic conditions. Okay, now we are saying that if we want to show that R is in the algebra, for us to show that R is in the algebra, by definition, if this is already an algebra, then the empty set is already what? In that algebra. Now since the empty set is already in the algebra, by definition too, the complement of the empty set must be in the what? Algebra. So this implies that what is the complement of the empty set? R is also what? In the algebra. Okay, so that is how we solve for the first one. Now for the second one, we know that if AB, second one says if AB is in the algebra, then their what? Finite intersection is also what? In the algebra. Now if A and B are in the algebra, then this implies that if A and B is in what? The algebra, then this implies that A complement and B complement must also be in the algebra by definition. Remember, we are saying that this is an algebra. We are trying to prove this proposition. Okay, so I've done showing this. It's remaining these two, right? Now if A and B is in the algebra, then by definition of algebra, its complement must also be in the what? Algebra. Now since these two are in the algebra, since this one is also in the algebra and this is also in the algebra, then its finite union, A complement union B complement, must also be in the algebra. Because we are saying if this is in the algebra, this is also in the algebra, then the finite union must also be in what? In the algebra. Go to the condition 3 here, where we say if these two are in the algebra, then their finite union must also be in the what? Algebra. So we use that logic there. Now if these two are also in the algebra, remember De Morgan's law. Okay, so De Morgan's law says that this is the same thing as, but A complement union B complement is equal to what? A intersect B complement, right? From De Morgan's law, right? Set theory from De Morgan's law. So what does this actually imply? Means that this implies that A intersect B complement is in the what? Algebra. Now look at this. If this is in the algebra, what does this imply? It means that the complement of this thing you are seeing here is also in the algebra by the second property. If E is in the algebra, then E complement is in the algebra, right? So if this thing you are seeing here is in this algebra, then the complement of this thing you are seeing here is also in the algebra. So this means that A intersect B complement or complement is also what? In the algebra. Now whenever you have A complement, this is the same thing as A in set theory, so therefore A intersect B is in what? The algebra. So we have shown that the second property is also true. So if AB is in the algebra, then A intersect B is also in the what? Algebra. That is, the finite intersection is also in what? In the algebra. So this is also true if you extend it to this I equal to 1 to n, I equal to 1 to n of AI is also what? In the algebra. If you extend it, it is also true for this, okay? Meaning that it might not necessarily be two sets, it might also be a sequence, a finite sequence or finite sets, okay? Now, the last condition, the last proposition, which is number 3, if AB is in the algebra, then A difference B is also what? In the algebra, okay? That this is A difference B is also what? In the algebra. That is difference of two sets is also in the algebra. Now watch. Now observe that if AB is in the algebra, then this implies that A complement is in the algebra. This implies that A complement is, don't mind my handwriting, is in the algebra, and also B is also in that what? Algebra. So if AB is in the algebra, it's by the property 2, A complement must be inside the algebra, and also B must also be what? In the algebra. Okay, but since these two are in the algebra, since A complement is in the algebra and B is also in the algebra, then A complement intersect B must also be in the what? Algebra. Okay, A complement intersect B must also be in the what? Algebra. Okay. Oh, sorry. What? Let me do this. Let me do it this way. This is actually true, but I want to arrive at A difference B. Okay. So let me actually put this to be B complement. This is also actually true, but I just want to arrive at A difference B. Okay, sorry for this. So this is going to be A intersect B complement. Sorry, you can also use the other method. If assuming I left this to become A complement and only B, then I will arrive at B difference A, okay, which is also in the algebra, but I want to arrive at this from my proposition, so forgive me. So here now I'm going to have A intersect what? B complement is in the what? In the algebra. Remember, we have shown that finite intersection is also what? In the algebra. So I use that proposition to solve this. So their finite intersection is also what? In the algebra. Now, but what is A intersect B complement? A intersect B complement is simply equal to A difference B. That is the definition of difference of two sets. Okay, so this implies that A difference B is in what? In the algebra. Okay, so you see I've proven my what? My three propositions and shown that they are all what? Algebras. That we have shown that the set of real numbers is in the algebra, then if these two sets are in the algebra, then their finite intersection is in the algebra. If these two sets are in the algebra, then their difference is what? In the algebra. Also, like I said, if I should have gone with A complement, then I will arrive at what? B difference A, which is also what? In the what? Algebra. Now, finally, the symmetric difference of two sets, A symmetric B, which is defined as A union B difference A intersect B, which is also defined as A difference B union B difference A. This symmetric difference is also in the algebra. Because how is it in the algebra? This is a simple logic. If the union of two sets is in the algebra, the finite union is in the algebra, and the finite intersection is also in the algebra, then their difference, since this is in algebra and this is in the algebra, then their difference must be in the what? In the algebra. So this makes this to be in the algebra. Remember, this is either defined as this or you define this as this. Now also, if I'm defining this to be this, then difference of A difference B is in the algebra, right? B difference A is in the algebra, right? So definitely, if this is in the algebra and this is in algebra, then their finite union is also in what? In the algebra. So this makes the symmetric difference to be in the what? In the algebra. Okay, so thank you guys for watching this video. Please, I hope you understand what I did, and if you don't understand, try and watch it again so that you get the full gist of this video. Thank you very much. Please don't forget to subscribe and like and share it to your friends. Thank you.